Okay, so we have worked through a few examples of graphing polynomial inequalities. I have one more example of the polynomial version, and this one I'm calling my special cases or my special examples. And we're going to see why it's special here in a second. So I have four problems, but in essence it's the same problem. We just need to interpret the answer four different ways. So we have 4x squared minus 12x plus 9, and then all the different inequalities set up next to 0. So I want you to pause the video and work these on your own and see why this is a special case and see why each of these have different and unique answers. Okay, so I'm just going to start this all at once, and I'm just going to treat this as 4x squared minus 12x plus 9 is equal to 0, and then I'll change my inequalities after I get my number line done, and I'll just select the appropriate answer from there. This is a degree 2. I can solve it by factoring quadratic equation, completing the square. Again, I always like factoring. It's the shortest and easiest process for me. So this is a duplicate answer. 2x minus 3 times 2x minus 3, or if we want to condense it like we saw in the last example, 2x minus 3 squared. All right, now I need to set this equal to 0, so I just take my inside factor and set it equal to 0, and that gives me the solution of x equals 3 halves. So that's my only x-intercept, or my only 0 or boundary, whatever word you want to use for that. I'm going to put that boundary on my number line, and then we have to test the intervals on both the left and the right to see whether it's positive or negative, or above or below the x-axis. And we're looking for all different variations of the answer here, so we need to fill out everything. Okay, so I'm going to do my chart here where I pick two x values for my two intervals. On the left, I'm going to put 0, because 0 is the easiest number, smaller than 1 1/2. And on the right, let's just pick 5. But again, anything larger than 1 1/2 will do. We need to plug this in any one of these versions over here, but as I always suggest, the most factored version is going to be the easiest. So that's the one I'm going to plug it into. 2x minus 3 squared. Okay, so let's plug each of these numbers in. Now remember, I really don't even have to do any work here because each of these are squared. And just like in the last example, when we have something squared, it doesn't matter what the sign is initially because it's always guaranteed to be positive. So over here, this is positive or above the x-axis, and same thing over here. This is also positive or above the x-axis. So both of these are greater than 0. Okay, so that means this spot here is the only part where it's equal to 0. Our boundaries is where it's always equal to 0. Now, if you want a visual representation of this, no big deal. Always just get out your graphing calculator or the Desmos, and we can just graph this just like normal. And so I have the graph of y equals 4x squared minus 12x plus 9 graphed over here. Of course, it's a parabola because it's degree 2 opening up because my leading term is positive. And just like we saw on the sign chart, it's equal to 0 here at 1 1/2, and every other part to the left and to the right of it is above it. Okay, so we know that we have the right answer. Now what we need to do is we need to select the appropriate intervals for each of our examples over here. Let's start with the easiest one here, where it is greater than 0, because that's what I have on my sign chart. So I have it's greater than 0 on the left, so negative infinity up to 3 halves, my leftmost interval, and then it's greater than 0 on the right, so 3 halves to infinity. So basically the only part of this graph that is not greater than 0 is right at the boundary, right at my vertex right here, because that is where it is equal to 0. And we're going to put a union in between. Okay, so let's go to the other variation of this, greater than or equal to 0. So if the left-hand side of my graph is greater than, the right-hand side of my graph is greater than, and in the middle it's equal to, that means that this graph is always greater than or equal to 0. So in set builder notation, you would say every single number from a negative infinity to infinity, or another answer of this that you might see is all real numbers. Okay, now let's go to the less than parts of this. So where is my graph less than 0 at? Well, it's not less than to the left, it's not less than to the right, it's not less than in the middle, so that means we don't have any place where this graph is less than 0. So our answer might look something like no solution, or sometimes we use this symbol to represent the empty set, or if you're actually looking in set notation, you might just use your braces with nothing in the middle, and so that is another way to represent the empty set notation. And then the last part is where is it less than or equal to 0? Well, we already said it's nowhere less than 0, but we do know there's one spot where it is equal to 0, and that is right here in the middle. So the only answer that we have there is at our boundary point, and so that is when x is equal to 1 1/2 or x is equal to 3/2. So you can see why this is a special case is because our vertex lands right on the x-axis. And so we can see that each one of these variations of our inequalities here have completely different answers. Okay, moving on with graphing rational inequalities, and just as I promised, I have a special case example. So just like I did with the polynomial special case, it's all the same example, but we see all the 4 different inequalities. So I suggest that you pause the video, see what answers you come up with, and see if you understand why this is considered a special example. Okay, so I need to talk about domains, so I don't forget to include my vertical asymptotes, which means I need to figure out where my denominator is equal to 0. So if I move my -4 to the other side, and if I were to take the square root of this, that would mean that x is actually going to equal positive or negative 2i. Well, I is imaginary. It doesn't make sense. We cannot graph it. So that means that I actually don't have any vertical asymptotes. So I don't have to worry about those. I don't have to put those on my number line or sign chart or whatever the case. Okay, so then I can just solve this one where this problem is equal to 0. So if I just took my fraction as is and set it equal to 0, I know I can very easily get rid of the denominator by multiplying it on both sides. Cancels it out over here on the left. On the right, 0 times anything is 0. And the only time that x squared is going to be 0 is when x itself is just 0. So that is my intercept or boundary. So that's the only number that I need to put on my number line. Okay, so let's see what's happening on both the left and the right-hand side of this number line. So I'm going to pick my x values as something smaller than this and something greater than this. Well, my smaller than it, I'm just going to plug it into my original equation. Gives me -2 squared over -2 squared plus 4. Well, on the top, anything squared is positive. On the bottom, I have anything squared is positive plus a positive number, so that is going to be positive. It means it's going to be above my x-axis there. If I do the denominator, I have all positive numbers, so that's also going to be positive or above my x-axis. So this is very similarly going to shape up the same way our special case example looks like in our polynomial videos. We have one point where it is touching 0, so this is where it's equal to 0, and then every other place is above the x-axis. And again, if you are a visual person, then why not reference the visual to this example? So let's go ahead and graph it. So I have it graphed here, y equals x squared over x squared plus 4. We can see that it intercepts our x-axis at 0, and we can see that it is above my x-axis every other place. Okay, so the easiest thing the easiest inequality for us to find is where it is above the x-axis. It's above the x-axis to the left of 0, and it's above the x-axis to the right of 0. And so we can see that on our graph here, above our x-axis on the left and above our x-axis on the right, but not in the center because that is where it is equal to 0, and we don't have an equal to in our inequality. So if I wanted to look at the greater than or equal to part, I can see it's greater than on the left, greater than on the right, and it's also equal to in the center. So every part of this graph is greater than or equal to 0. So I would say from negative infinity to infinity, or maybe all real numbers. All right, so where is this graph strictly less than 0? So anything below the x-axis, there's no place where this graph is less than 0. So I might say no solution, or you might answer the empty set. And then where is this graph less than or equal to 0? Well, there's no place where it's strictly less than 0, but there is one place where it is equal to 0. And so the only answer there is when x is equal to 0 itself. So you might want to put that in set builder notation, so x such that x is equal to 0. Okay, and so again, you see why this is special cases, because it's mostly all above or below the x-axis.